Hey everyone, welcome to our next section. We're going to start to go through some ideas of gravitational force as well as connect that together with friction and kind of wrap up our kinematics and dynamics section. So to start off with gravitational force in the Earth's surface, same thing as before. I encourage you to pause and jot down any notes along the way that will help you kind of understand the concept and try out any questions along the way as they come up. So to start off with, we have this idea of a force field. I know this has kind of come up before in popular culture and that kind of stuff. But this idea of a force field is this space that surrounds an object, in which the object can exert a force onto other objects. So if you think of like a magnet, for instance, and you place objects of either the same pole or opposing poles to that, then they will either repel or attract, and based on the distance that you are away, the weaker that pole or that attraction becomes. So this means that every mass actually feels a force pulling it toward the Earth, if we think about kind of how gravity works. So the gravitational field strength is the amount of force per unit mass that acts on objects in the gravitational field. The further away an object is from the center of mass, or center of the Earth in this case, the weaker that gravitational field strength will get. So it's a vector quantity that has the direction downward or toward the center of the Earth, and its SI units are in newtons per kilogram. Now, newtons per kilogram is kind of something that we can manipulate, and I'll show you that in a second as well. So here we have kind of a picture of what the idea looks like. Remember that whenever we draw these arrows, they're really like vector lines all pointing in toward the center, and from our kinematics unit, our vector lines actually can be drawn to scale. So you can see our kind of longer vector lines are all the closest ones to the Earth. They experience the greatest gravitational field strength. And then we kind of have these outer second tier ones that are still a little bit longer, but they're definitely not as long as the first group, and they're a little bit more further distance away, and so their gravitational field strength is a bit weaker. And then our third tier outside ones are even weaker still, because they're getting further away from the Earth's surface. These are kind of a gradual decrease in field strength that doesn't just jump from one to the next. So it just depends how far you are away from the Earth's surface. Okay, so just kind of an idea of gravitational field strength. So a simple way to measure the force of gravity is to hang mass from a force scale or sensor. And so if you haven't had a chance to do the activity yet, measuring force scales, this would be kind of that time to pause this. Make sure you do that activity before you do come back and kind of continue on, just to give you the idea of what force is as it starts to be pulled downward, and using those force scales. So if you've done that activity, then you're okay to kind of move on into this section. So there's a link here, but I'll let you kind of click on that on your own. But basically it just goes to a conversion table that connects a mass chart to a force of gravity chart. And so we have your force of gravity, it's in newtons, it's pulling downward, and your mass is in kilograms. And basically you're just plotting out a few different points. So again, you'd make this chart on your activity that you would go through with the force scales. So again, just to kind of go through and kind of run through that, just to come up with a general idea, general comparison of mass to force, but you can certainly click on that link and see how the two are connected in terms of kilograms and newtons. So as you graph this out, from that activity, what you'll start to put is your force would really be your y-axis and your mass would be your x. And so we would create this kind of chart, or this kind of idea, that would really have force on your y-axis and then your mass on your x-axis. And so we have this idea of newtons over kilograms for a unit. And as you start to plot out points, you're going to notice that they all follow a linear pattern. They all follow a straight line. So using that idea, then kind of ask a couple of questions to really understand, okay, what's happening here with a force to mass comparison. So the slope of this line is going to be a ratio of force to mass. Okay, so remember when we talk about slope, slope is really just rise over run, or in this case, it's talking about force, because force is our y value, it's our rise part, and our run, our x value, is going to be mass. And so, what do we have for a unit here? Well, really, we have newtons per kilogram, which is that unit that we started off with when I mentioned the SI unit before. So there is a neat kind of relationship to this Newton per kilogram unit because we already have an idea of what a Newton stands for, right? 1 Newton is equal to 1 kilogram meter per second squared. So if I take this unit, a kilogram meter per second squared, and I sub it in for the Newton's value that's up here, I'm going to write out the division marker kind of a different way, like we're used to seeing divide by, and then I'm going to put kilograms on the bottom. Now really remember what divide by means is that this is over 1, and so we flip and we change that to a multiplication because it's a fraction. So I'm going to flip this, change it to a multiplication, and flip my fraction. Now what I see is that kilograms cancel top and bottom, and I'm left with meters per second squared. So I'm left with this. And what is that unit? Well, that's an acceleration, which really implies, in this case, of force and gravitational field strength. This is acceleration due to gravity. And so, really, we have this connection between gravitational field strength and what we understand gravity to be so far in an acceleration. So, since the gravitational field strength and the acceleration due to gravity are both numerically equal to each other, because we can see they share the same units that are up there, the same symbol for gravity gets used. And this isn't something that I don't want to labor on too much. It's just using our letter G with an arrow over it to indicate that it is a vector quantity. So, example 1. Says the maximum train load pulled through the channel, which is this train tunnel underneath the English Channel that links England and France. The max load that it can take is 2,434 tons, or where 1 ton is equal to 1,000 kilograms. So determine the force of gravity that this max load would apply to the channel. And so it wants to determine the force of gravity. And so we've talked a little bit about force of gravity before. It's just Fg. And so we're going to work through this one together and just kind of go through how these problems are set up. They seem like there's a little bit of new information, but really we're just reusing old things that we've kind of already talked about in previous topics. So the main thing here is we have this mass value, 2,434 tons, where a ton is equal to 1,000 kilograms. So we need to figure out in total what that mass value is going to be in kilograms, because we're going to need that to figure out our Newton value for the force of gravity. So when we solve this, we have this mass so far, that's 2,434 tons. And we know that there are 1,000 kilograms per 1 ton. So I can see top and bottom here, tons are going to cancel. And then really, I have 2,434,000 kilograms. So that becomes my mass. Then we have this, wants us to find the force of gravity. And so, in order to find the force of gravity, we have to make a connection to how we calculate force. Newton's second law says that any force can be calculated if I take the mass and multiply it by its acceleration. Well, in this case, we have this special scenario where the acceleration is really caused due to gravity, and so I have my formula indicating that the force of gravity can be found by taking the mass and multiplied by the gravitational field strength for that value. So really this is just saying Fg is equal to mg. So force of gravity is equal to my mass value, which is 2,434,000 kilograms. And then I have this gravitational value pulling downward or pulling toward the Earth at 9.8 meters per second squared. And so my force of gravity in this case is going to work out to be 23,853,200. And if I put my units together here, I have a kilogram meter per second squared. And so my force of gravity, if I take a look now for significant digits in this thing, the gravitational value is constant, it's 9.8. And so really I'm looking at 4 digits here, the 2434, and so I'm going to have, in scientific notation, 2.385 times 10 to the 367, if I just count my jumps over, kilogram meter per second squared. And then really, because I have my gravity value, this thing's negative, the direction here is downward. Okay, so that's just being able to calculate what gravitational field strength looks like. So, I'm going to pause the video here, and we're going to come back and talk about mass and weight in the next video. So, hopefully that was a good little intro just into how gravitational field strength is calculated.